Yeah, so yeah, I can send you the last couple 3 years of exam problems or something like that. Yeah, I'm happy to do that. I'll try and remember to do that today. So, yeah, I'll put them on Canvas. Okay. All right. So we've been talking about solutions to Laplace's equation, and in particular, last time we talked about the mean value property, which essentially says that any harmonic function should satisfy the mean value property. So just because I think it warrants noting again, I will write it again. So so from last time, we talked about the mean value property. And essentially, this just says if well, let me make sure that I formulate this just right. Okay, so U is C2 on some domain omega and harmonic, okay? If and only if for any ball B with a center at X and a radius R, which would be all the points Y in Rn, such that X minus Y is strictly less than R, and it's a subset of omega. And then we have that U of X is equal to the average over the shell of this ball, or the surface of it, as well as the volume. Okay, so this is going to be helpful for allowing us to prove a maximum principle, which we're going to do now. And in general, it's also useful for getting bounds, uniqueness, size estimates, many different applications to harmonic functions. Okay, so at the end of last lecture, we wrote down the maximum principle, which is if we let omega be open and bounded, and then we suppose that U lives in C2 on the open set omega, and then it's continuous on the closure. And again, it'll be harmonic in omega. Then the following two things are true. One is the weak maximum principle, the other is the strong. Now, the weak maximum principle says that the maximum over the closure of omega of U is equal to the maximum over the boundary of U, of omega for U. The strong maximum principle is stronger, and it says that if omega is connected, then one of the following things is true. Either U is just a constant on the closure of omega, or U is strictly bounded from above by the max on the boundary for any X that lives in omega. Okay, so I've written this down before last time. Okay, how are we going to prove it? Well, we start by proving the strong form. Okay, and then the weak form, you can show that it follows from this. Okay, you might expect. Okay, so what do we start with? Well, we suppose, okay, that omega is connected. And we're going to build a contradiction, okay? So we're gonna assume that there exists, okay, some x0 that lives in omega such that u of x0 is equal to the max over the closure of omega of u. And we call this thing m. Okay, so we're going to show that this can't be so. So how do we do that? Well, we're going to leverage the mean value property. Okay, and the mean value property allows us to say, well, now if we choose some r such that we have a ball that lives in omega, okay, then by the mean value property, we have that the following must be true. U of x0, which is equal to m, should be equal to the average over the volume of u, okay? Over the volume of the ball of u, okay? But what can we immediately conclude if we put these two things together that we've assumed? Okay, well, because u at x0 needs to be the max, right? And that number needs to be the average of some, ball within our domain. Every single value within that ball also needs to be equal to m, because we can't have any values in there that are bigger than m, okay, which would allow us to have values in there that are smaller than m, okay? So the only way to sort of accomplish this is to just have the whole interior be m, okay? And maybe now you can see how the rest of this proof is going to unfold. I'll still write it out. But essentially now, all you do is now you take this ball and you sort of you sort of bootstrap or you daisy chain all these balls together, and you cover the domain, and you say, well, now that means, basically the rest of the domain needs to be constant as well. Okay, so that's where we're going with this. So basically, but u of x in general needs to be less than or equal to m everywhere. Okay, so it must be that u of x is equivalent to m throughout the ball, b of x0 r. Okay, so s equal to x in omega such that u of x is equal to m. Okay, well, now we know that this set is going to be made up of at least that ball and maybe more such balls. Okay, and those balls are non-empty and they're open. Okay, but we can also show that S is also relatively closed, okay, in omega. Okay, how do we know that? Well, essentially, to show this, we're going to let xn, which lives in S, converge to some other x in omega as n goes to infinity, so we're trying to build up a closure property, okay? Then, well, because of continuity, right, u of x, because everything in here is constant, is equal to the limit as n goes to infinity, xn is equal to n, right? Because we have continuity of u. So any limit like this must be, equal to the actual value at that point, okay? So any limit that you take from within S needs to also converge to that u is valued at m at that point. So that means that we can now close the set S, right? And so we have a set that's both non-empty and open, but also relatively closed, okay? Essentially by continuity, okay? And now you say, well, how can that be? Well, we have a set that's relatively open, non-empty and closed. Well, the only non-empty, open, and closed set in omega is what?
Omega.
The whole enchilada, right? So is omega itself, okay? So, great. So S is just equal to omega, okay? So this was essentially the idea that we have some open set, right? It's going to contain all these constant points, but then because of continuity, we can just essentially keep spreading that set out until it covers the entire set that we're working with, right? So this implies that, well, u is just going to be constant on, in fact, the closure of omega, okay? So that's what we wanted to prove, okay? If that's not the case, right? Yeah, then we have to. I'll write down the sort of side case for that. But if that's not the case, then that means that u of x is strictly less than the maximum on the boundary. Okay. So the weak form follows from this. Okay. Because if the strong form holds, right, then we can always sort of relax that, okay, and get the weak form, okay, and then the minimum principle is proven by studying minus u, okay, and then the disjoint set case, I'll write on the next slide. Let me take a breath on this slide so you can take a breath too and finish. Are there questions about this? Okay. All right. Can I move on? I don't want to advance the slide before everybody's done. Okay. I think I see some head nodding. So that's the maximum principle. The side case of this, right, is, well, let's say if I have some disjoint set, right, which is the union of two connected sets, right? So I have omega 1 and omega 2. Obviously, then you can't daisy chain together these open balls, right? Across the separation between these disjoint sets, okay? And so in that case, we see that, well, if we define u of x is equal to k on x in omega k, well, then u is harmonic, okay, but does not satisfy either strong form conclusion, right? So what you can say then is that within each of these disjoint sets, we can prove this, that either U is going to be constant, right? Or the max is obtained on the boundary of each of the disjoint sets for that particular disjoint set, right? But the global max, right? You could have values in this that are bigger than the max over here, right? So that's the main consequence in that case. Okay. So